Imagine a liquid that defies expectations, a substance you can pour yet control with a magnet. Here at Dendro Zap, we break down such fascinating concepts, and today we're diving into the mesmerizing world of ferrofluids. These aren't just any liquids, they're incredibly responsive to magnetic fields, morphing into stunning, often spiky, shapes. This unique interaction opens up a realm of scientific wonder, showcasing how even seemingly incompatible properties can coexist. It truly looks like something out of a science fiction movie, but it's real science in action, right before your eyes. So, what exactly is a ferrofluid? At its core, it's a colloidal suspension. This means extremely tiny ferromagnetic particles, typically iron oxides like magnetite or hematite, are dispersed evenly throughout a carrier fluid, which could be water or an organic solvent. These particles are incredibly small, often just nanometers in diameter, about 100,000 times smaller than a human hair. This nanoscale size is crucial because it allows the particles to remain suspended indefinitely without settling, even under gravity, forming a stable liquid. But why don't these tiny magnetic particles just clump together when a magnet is nearby, or even just attract each other? This is where a clever chemical trick comes in. Each nanoparticle is coated with a surfactant layer, acting like a protective shield. This surfactant, often a long-chain molecule, prevents the particles from aggregating. Instead, they remain individually dispersed, free to move within the fluid. This crucial layer ensures the ferrofluid retains its liquid properties while still responding dynamically to external magnetic forces, allowing it to flow smoothly. The most iconic behavior of a ferrofluid is its spike formation when exposed to a strong magnetic field. When a powerful magnet is brought close, the liquid's surface erupts into an array of sharp, mesmerizing peaks. This phenomenon, known as the Rosenzweig instability, occurs as the fluid attempts to minimize its magnetic potential energy. The peaks align themselves along the magnetic field lines, increasing the surface area exposed to the field, thereby optimizing the magnetic attraction. It's a beautiful, dynamic demonstration of physics, where magnetic forces overcome surface tension and gravity. Ferrofluids aren't just a captivating desk toy, they have several practical applications. They are used in high-fidelity loudspeakers to dampen cone movement and dissipate heat, improving sound quality. They also find use in seals for rotating shafts in hard disk drives, preventing contaminants from entering while allowing smooth rotation. In the biomedical field, researchers are exploring their potential for targeted drug delivery, guiding medication to specific sites within the body using external magnets. These diverse applications highlight their incredible utility beyond mere novelty. From industrial applications to cutting-edge medical research, ferrofluids continue to intrigue scientists and engineers alike. Their unique blend of liquid properties and magnetic responsiveness makes them a versatile material with ongoing potential for innovation. Think of frictionless bearings, advanced sensing devices, or even miniature robotic systems that can navigate complex environments. The future of these liquid magnets is as fluid and dynamic as the material itself, promising even more astonishing breakthroughs. That's the science, now you know. Stay curious. Dendro Zap, out.